Welcome back everyone, and in today's video we're going to explore more bump mapping. Previously on the subject we dealt with height maps. Today we're going to deal with normal maps. And normal maps, as you can see what I have in the background, is a very bluish texture, and these textures contain normal directions that helps us control which direction each pixel in our 3D model is going to have the light bounce in what direction. Or what part of that model, when we're rendering that fragment, what direction that the light should be pointing, or that what its normal direction is. And the whole point of these normal maps is to create depth, kind of like how this example, the texture actually gives it more of a 3D look based on how you apply light and darkness to it. So we're going to use normal maps. And normal maps are normal directions that are saved in a way, and it's kind of saved in this other coordinate system called tangent space. It's kind of like model space and view space and everything we've done in WebGL and dealing with 3D. Normal maps are stored in tangent space. And tangent space is a relationship between the normal direction that these textures come from and then the UV coordinates. So UV coordinates is the flat, up, down, left, right. Then the normal direction is actually the z-axis. So that's, and the z-axis is stored in the blue channel. And that's why you notice that all the textures are very bluish, because they're normal maps, and normals are stored, the z direction of normals are stored in the blue channel, hence why everything is more bluish. So let's go talk more about tangent space. And tangents, like I said, tangent space is just a way to really just store it into a 2D form, because when you create because there's two ways you can create normal maps. You can use a height map to generate your normal map, or you can bake a normal map based on a 3D model. And when you create 3D models and you want all that high detail look, sometimes you'll model a high detail version or high resolution version of your model. It has all the little dimples and creases and cracks and whatnot. And then you bake that into a texture. And what it does is just takes the UV coordinates into your 2D texture, and then interpolates all that 3D normal direction onto a 2D plane. But to do that efficiently, where you can reuse this texture on anything, not just the model it was created for, you convert everything to like tangent space. So it lives in this different coordinate systems, so it can be reusable on any mesh and not just the mesh it was originally created from. And in that analogy, once you have that high resolution model that you baked all those normal directions into a texture, you can then use a low poly texture, low poly model, and apply this texture to it, and it kind of looks like that high poly version of your model. That's one optimization trick to kind of get better looking models, but using low poly models. So it's by creating a high poly model, baking all its normal directions into the normal texture, and then using that on your low poly. And that's really how a lot of this works. And then when you see in games with really high detail, the cracks and the dimples and some of that things that make things pop so it's not so flat, it's really based on normal maps. And sometimes, like I said, they're baked from high resolution 3D models. So let's talk about like tangent space. And so this is a really bad circle, right? And just pretend this is our 3D model of a sphere. So we're going to try to render a sphere, and we're going to wrap our model or our normal maps around it. So our circle has its own normal direction. So we need to convert that normal direction into the normal that's technically in the actual texture model. So you kind of have your own texture model, texture that essentially has all these pixels, and all these pixels point in all these different wacky directions. and they go in all different directions. They can go forward, or they technically can go back as well. So we need to translate the normal that exists in tangent space into world space. And to do that, you basically the process of creating that texture, you kind of have to do the reverse. Like I said, the 3D, like let's say this is a 3D model, it has a normal direction. That normal direction is then calculated in a certain way along with the x and y of the texture. So the texture has a UV coordinate. So that UV coordinate system is used to help take this normal and put it in there, which then kind of creates that extra direction that goes in whatever normal direction you want to go. So you basically have to reverse it. So you're going to have to reverse the calculations to get that back out into world space. And the way you do it is that once you have to use your own normals, and it's basically based on the face. So you have a triangle. So a face of a triangle has a normal direction. So we need to calculate this plane, because that's what a tangent space is. It's a plane, really. So you have this, and if you remember correctly, a plane is defined by a point and a direction. So we have a point. This is our fragment point, and that fragment does have its own normal direction. So at that point, we can then create a plane based on, this is a very bad plane, it's easier if I just create a plane first. Create a point, and then make a point that actually points in that right direction. So you have a plane, essentially. So that's what we're trying to do. So that plane, once we calculate that plane, allows us to translate this into our world space, or convert back into it. Because that's the thing. Because but there's 3 different ways we can go about doing this, and we'll explore all different ways. And the first 2 ways you go the same route, where we actually convert things into tangent space, and we do all our math. And it's an optimization thing. And then in our final example, we go the other way, and we use it's completely different type of code, and we take our normal direction, and we bring it into world space, and then we apply it into our regular math for lighting, our regular lighting math. So to determine this whole tangent space, we already have the one direction, but we need these other 2 directions to help us define tangent space. And this is it's the same thing as the UV coordinates, but it's more in the 3D direction. So since we already know that direction, we kind of need to determine this direction and that direction. And that is sometimes called the tangent and the bitangent, or the tangent and the binormal. It just means when you see the bi part, either bitangent or binormal, they're the exact same thing. There's just the other direction other than the normal that you need. And to do all this transformation, you need a transformation matrix, or the 3x3 transformation matrix. And I know throughout the series we've used, I keep kind of telling you that you can always pull the direction out of your rotation matrix. When you do your rotation matrix, each column denotes the norm of the left, the right, the up, and the forward direction. And if you normalize it, you can use that into actual direction. And it's the same thing with how do you calculate the look at function. We've done that, I think, a long time ago, where we kind of explored the rotation look at function, where you use the up direction and then the direction you want to look at, and then you end up calculating the remaining left, right, and the new up direction. So the forward, the left, and the up direction. And then we save that into a matrix, and that's really what a rotation matrix is. It's just 3 directions. Those 3 main directions of our 3D. So that's really the gist of tangent space. It's really just a rotation matrix of a custom direction, custom direction, or custom coordinate system with its own direction, basically. Like I said, each pixel technically will have its own. When it's on a triangle, technically they should be all the exact same matrix, but it's only for that one triangle. When you move to the next triangle, that has its own plane, and that plane will have its own tangent space. Because, like I said, it's just based on that point and the normal direction. And since every point does have its own normal direction, so even the face is different. Even if it's the same triangle, when you're interpolating all the pixels, you might have different normal directions. But if you normalize it, if you're doing smooth shading, then they will have normal, their own little normals essentially. If it's flat shading, then they should have normals for every single triangle. But so if you're doing more smooth shading, it's going to be different. So we have to so you have to figure out what the tangent and bitangents are, and once you have those three directions, you can make the matrix, and once you have that matrix, you can then transform things back and forth. All right, so let's look at some code. So we're going to look at the first example. The first example, we're going to create a 3D matrix, right? So first, we're going to figure out how do we get all this information, right? So normally we have the normal direction when we come through the amount. So we need to figure out our tangent and our bitangent. So I have a nice big old function or class. I create normal spacing, normal mapping, and has all this fun stuff. It's quite a bit of code if you're going to actually calculate everything yourself. If you have a 3D modeling tool, sometimes they have the option of exporting the tangents along with the normals. So this way you don't have to do any of the math yourself. And you can also, once you have the normal and the tangent, you can actually calculate the bitangent in your shader itself. So you don't need to actually store all three information. You don't have to calculate all 3 bits information. In this video, we're going to calculate everything. Because if you know how to calculate everything, you can start cutting things out if you don't need them. So it's basically to cover the bases. If like this example, you doing everything. So this is a great example of how to do it all. So it's a simple model. We calculate our quad, and we just start calculating our TBN, tangent, bitangent, and normals. I like this. This doesn't even have I don't have normal data here either. So I'm just calculating it all. So we start off with this first function, and like I said, when we calculate a plane, you take a triangle and you take the 2 edges, and then from those 2 edges, you can then start using the cross product to end up calculating everything, and that's essentially what you're doing for the most part. But it's slightly different because of you're trying to create something for tangent space. So this is the equation really that defines tangent space. It's the UVX times tangent plus UVY times bitangent equals edge 2 and whatever. So essentially, these 2 equations get rewritten in a certain way. So because the T and B's are unknown, but the edge 1, edge 2, and your UVs are known. I know how to rewrite equations based on 1 unknown. I don't know how to rewrite equations based on 2 unknowns. So I can't really explain how this equation gets converted into these 2 other equations. And these are incomplete equations, by the way, because this gets rewritten into a division, and this is the denominator of that division, minus this part. This part, this is the part that actually is the denominator of the division, and these are the numerators. So you have to take this, like this, divided by this, gives you tangent. This divided by this gives you the bitangent. So those are the 2 equations written in JavaScript form. This, I'm inverting it so this way I can do multiplication. So I can use scale very easier. So it's easier to multiply and then do division. So that's why I have, and it's a shared denominator. So, and I'm using it more than once. So why not just convert it into do the division once and then apply it as many times as I need it as a multiplication. So once we have all our edge information and all the UV information, I've done this before and so many times in the videos. There's no reason for me to explain how to do edges and planes. But I guess just for a quick recap, if you have point A, B, and C on I guess I should just be easier to just draw it. As they say, it's show, don't tell. So you have your quad, and you have A, B, and C. You have your points. So if you want to do your edges, here's edge 1, and this is edge 2. So it would be B minus A, and then C minus A. And that would be your edge 1 and edge 2. That creates the 2 points, and then when you do a cross product of it, it actually gives you the 90-degree angle and the angle of it. So this, and then from there, once you have that, you can then start. You basically start creating your directions. So you have you already have your normal direction. You already have your binormal, and then by another cross product, you're good to go. So that's what's all happening here, but we're doing it twice. We're doing it for the vertice edges, and then we're doing it based on the UV as well. So we need both, because that's like the original formula. It's based off of UV. So like I said, UV0 or UV1 minus UV0. It's like I said, it's basically the edge equation, but done in a 2D form, which is technically it's all 2D anyway when you're dealing with triangles. But there you go. Then you end up calculating your tangent. You calculate your bitangent. That's what temp A is. Temp B. Oh yeah, it gets saved into B. Gets saved into T. I was like, where's everything being saved into? So these are the final versions. And then, like I said, by doing that cross product with the edge 1 and 2, you get basically your normal. So like when I illustrated that extra line I created going straight up here, that's basically our normal. That's the normal direction. And everything else that we calculate beforehand is our tangent and bitangent. And since triangles are saved, like here's an example, the normal direction of this point, you can have 2 normal directions, because if you do the edge calculation on this triangle, for this quad, these 2 points can actually have 2 different normals based on what these 2 side points are. They exist in 3D space. So because of that, we're just going to add up everything, and we're going to keep track of how much for that vertice we have, because then we're going to do the average. So once we're done calculating all the tangents and bitangents and the normals, we're going to have to go and then average it all out. So that's why we have the average count. So then that's why we're just adding it all together, because vertices are shared. So once we do that, you then do the average. So once you have all the information, very simple average, you just go right through and just average everything out. After that, you just normalize everything. And you basically just go through again and just normalize all the data. This could be like more optimized, essentially. Like normalize and average should be able to be done in the same function. I just separated them out as steps, so you kind of know how this all works. But like this is not the most optimized way of doing it, but this is the most efficient way of showing you all the steps of how this works. So normalize and average should really kind of be just merged together as a single function call. Since you're processing through all the vertices, after you average it out, just normalize it. and then you have your orthogonal handedness. This is a very complicated word for saying everything is 90 degrees of each other. So every direction in that we want to go in our x, I don't know what, y, z, every single angle between all 3 points is 90 degrees. That's what orthogonal means. So this function basically goes through every single, I think, face. Does it go through every single face? No, it doesn't go through every single face. I'm sorry. It just goes through every single vertice and then take these 3 directions and make sure they're orthogonal. And they there's some simple things. And handedness. That's an extra thing that I saw that you needed to do, just to make sure everything isn't cozy. So your direction isn't flipped by accident. So like forward, in case you have like a direction that's back, but it needs to be in forward. It's like inverted or something. That's what this does. It just makes sure everything is pointing in the correct direction. So if it's pointing in the negative direction, it's not pointing in the direction it needs to be. It needs to be all on the positive side. So that's what kind of handedness does. And then this part kind of just makes sure that things are orthogonal and save everything right back into your T. So once you have all the data done, then you can just dump it into your shader. Like up here, so once I have all the information, we dump it into our VAO, and tangent and bitangent will have its own buffer space. And let's see, so we'll go into our vertex shader. So we have a vertex shader, and we're going to bring in our tangent, bitangent, and normal. So like I said, normally you don't need bitangent. Once you have normal and tangent, you can calculate this yourself using a cross product. But like I said, I wanted to do everything for all. At this point, you can start pulling things out that you don't want or you don't need. And here's a function that ends up calculating the 3D matrix. And in case things are a little funky, you can try normalizing the data, but it should be normalized, because like if you're handling all the data yourself, you know it's normalized. But if you're getting things from like a 3D modeling tool, things might not be normalized. Sometimes they might have an option that says normalize all directions, and definitely check it to save yourself the hassle. But if you see that your lighting is a little wonky, you can try normalizing first as one way to troubleshoot. So that's why I kind of left that there, because I was having issues, and I normalized it, and that fixed some problems for me, and then I made sure the data came in normalized. That's why we have that normalization step. So once I normalized the data, I no longer needed to normalize anything anymore. Now the thing we need to do is that we need to rotate our TBN. So we pass in our model matrix, which is the rotation and scale and the translation, and we convert it into mat3 because we don't want translation. We just want really just rotation. So if we got scale in there, it's going to be in there a little bit. I don't know if I don't think that will screw anything up, but it might screw things up. But if it does, feel like it does screw things up, normalize it, because scale will then not make it not normalized anymore. So we just multiply our transformation matrix for each direction that we're pointing. So this way everything gets moved into world space, because everything right now exists in local space, in model space. So we move everything into world space, and we can just then create the matrix 3 once we have our 3 directions correctly. And we can do a transpose. And a transpose kind of just swaps the columns with the rows, which essentially, as long as the three directions are orthogonal, you can do a transpose. So this way it gets you the inverse of what you're doing. Because this matrix that we're creating right here goes from tangent space to world space. We want the inverse. We want to go from world space to tangent space because we want to move world space, our world position, and our light position into tangent space. So we can use the tangent normal with our calculations. So like I said, this is from tangent space to world space, and then as long as that's orthogonal, we can do a transpose which inverts it, so we'll go in the other direction. If it's not orthogonal, you can then use the inverse function, which does a perfect inverse of whatever the matrix is. It's just because transpose is faster than inverse, but you only get the inverse as a byproduct if everything is orthogonal. So I just want to make that very perfectly clear, because these small little details can really screw up your normals. So you have to know everything, and that's why I have everything commented. Because if something seems off, try the inverse or try normalizing, and if things are working, then you know that's what's going on. Like I'm kind of giving you some extra bits of code to help you troubleshoot your normals. Because like I said, this is kind of how I end up troubleshooting my normals a little bit. So yeah, once we have our transformation, we multiply our camera position, our light position, and our world position gets all translated into tangent space, and all of that gets sent into our fragment shader, and we pull out our normal. We just need to map it into, I think, -1 to 1. Because from the texture it's between 0 and 1, so we just remap it, we normalize it, and then we can use our tangent space values to calculate light. And that is really the entire process of using a normal texture. In a normal texture we're going to use this one. This one's actually, I found this one as a really good one for testing. So definitely if you're testing out normals and you're building this is probably one of the best textures I found that you can use for testing things out. And this kind of shows you why. And here you go. Here's a nice test of all that code. And this red point is the light source. So you can kind of see how this light, everything kind of just lines up just right. And I have several tests that you can run. So we can do that. Let's see what this one does. I forget. It's been a couple of weeks. Ooh. So as you can see, everything follows the light. So that means everything's working very, very well. Some of these are kind of fun. Up and down. Let's see what this one does. I forget. Refresh. So now you're testing to make sure the lights are working up and down. I think this one's a cool. This is zoom in and out test. Make sure that the light that's moving toward it and away from it works. So as it zooms in, it goes right into the center. So again, that's another good test. And I think there was one more test. Rotate around. And this one I have the texture, the light source spinning in like different ways. I'm spinning up around an X and Y coordinates, and I think I'm zooming in and out. Or no. Am I? No, I think it's staying on this side of the Z coordinates. All right, so it just spins around. So there you go. Yeah, work. Like I said, it took me a while, but I got it to work, and I got all these nice tests to really test it out. So that's how you do it with the matrix. Now I found this one cool example of one guy said he uses quaternions for everything. So I read what he does. And I managed to kind of put together an example of what he does. So it's actually the exact same concept. The exact same concept. The only difference is, because remember, we are calculating, we're taking the three directions and creating a matrix 3 out of it, right? So we're making a matrix 3 out of it, and then we're translating all the three coordinates into tangent space. That transformation matrix, all it is a rotation, and you can represent the rotation with a quaternion. So we can replace, like before I had tangents and bitangents and normals. Like I don't have any of that here. Just three values are now null, and I'm replacing it with a quaternion. So if you have 9 floats to represent your rotation matrix, you can then replace it with 4 floats by using a quaternion. And I have a new custom standard renderable, which just has a place for the quaternion TBN to come to quaternion. So like I'm not going to use this. Like I might use this as an optimization because this is probably better than having those 3 directions. Just having that quaternion is like, to me, is like you have less data and you have everything there. You have your normals, your bitangents, and your tangents. So I think I think it's a really great example or a really great idea the guy had. I should have the link in the description about how it's everything done. So like in the previous example, everything's the same. We still calculate all the tangents and whatnot and the normals. And the only now at the end, we actually feed all the information into a function that creates the quaternions. And it's actually pretty easy because our quaternion function has a function called from matrix 3. So basically, just dumping all our directions into the matrix, into a matrix, a 3x3 matrix, and then feeding that that matrix into this function, and it spits out a quaternion. So, like I said, it's what we're doing in the shader essentially, because we are creating this matrix. I'm just doing it on the CPU side, and so I can convert that into a quaternion. So once you feed that into a quaternion, you can just save that into your shader. So if I go here, so I got rid of all those vec3s, replace them with a single vec4, which is our quaternion. We have 3 functions here because OpenGL does not have any support for quaternion math. I'm surprised at this point in time that OpenGL doesn't have this built in, because that article or the blog post, how this guy uses quaternion for everything, you really do, because we use quaternions to save space and to speed things up when dealing with our armatures, because I don't create a 4x4 matrix. I use the quaternions, and we spit that into our shader, which is a lot less code, because if you have like 70 joints times 4x4 matrix, that's a lot of code. So in our code we use dual quaternions, which is just 2 quaternions together. One represents rotation, the other represents translation. So we take 16 floats and we convert it down to 8 floats. We half the data. So I'm kind of surprised that OpenGL doesn't have quaternion functionality built into it yet, since it seems like it's more and more it's being used. So that's why we have some functions in here for quaternion multiplication, quaternion inverse, and just how to multiply a quaternion on a vector to rotate it. And then we have another one called mat3 to quaternion. But just like remember in the last version, we need to move our rotation into world space, because our rotation exists in model space. So to rotate a quaternion, I need to multiply it by the world rotation, and there might be a function how to multiply. I didn't find one, but there might be a function where you can multiply a 3x3 matrix with a quaternion and have it rotate. I couldn't find one, so the only solution I can come up with was convert our mat3 into a quaternion and then multiply that model view, or that model matrix quaternion, against our tangent space quaternion, and that gives us our world quaternion tangent space uh, um, rotation transformation. And then instead of just, and we have to use a function to do the rotation, so we can't just say tangent times position, because they're both just vec3s and vec4s. So we have to use a function, and like I said, we use that world rotation of tangent space on our 3 positions, and then our fragment shader is the same. I think this one's probably a lot less code, well, somewhat, I don't know. Definitely a lot less data. No, this is only one function, where this one you need at least 3 functions. And I put a to-do where I can convert our model matrix into a quaternion and then have that come in. So that's one damn, I suck at English sometimes. Opposite. How to make things better and faster. Optimization. There you go. Optimization trick. So you're not doing it for every fragment. You only do it once, and it's one way probably to speed things up a little bit if you really wanted to. So that's the quaternion way of doing it. In case you really want to see, and like I said, we have to inverse it because it's tangent space to world space. So after we're done, basically you'll multiply quaternions together, but it's the same thing as the idea of adding them up. You actually multiply them, and then you do the inverse. So this way we can go into world space into tangent space. I have comments here that kind of explains it. Like I said, all these functions are actually really tiny. There's not really much when it comes to. Sometimes there's not much that comes to quaternions. So yeah, that's multiply, that's inversing a quaternion, and that's just multiplying a quaternion with a vector. So you can rotate the vector. In previous videos, I probably had something called Q rotation. So, but this is essentially, I think it's probably the exact same function, or I found a new one that's, I found a new one, but it basically, you have to have 2 functions. I think the function I had before was one function. All this math was actually part of this function, so it was a kind of Q rotation. And that's it. And if you really care, we can go into the quaternion version. And like I said, I don't have to go through all the tests because I already have. It works. So you can replace tangent, normals, and binormals with a quaternion and just do all the math in the shader with quaternions. Okay, so now we have the final example. The final example is probably what you're going to use for prototyping. So this way you don't have to do all this extra math and stuff. It's completely shader, and it's completely in the fragment shader. So I found this one example of how to do it completely in shader. And don't remember what it looks like. Should have loaded this up. Oh yeah, so it's just a quick example, just a quick code on how to create that transformation. I think I probably just did one little tweak to it. Yeah, I did one or two little tweaks to it. The only difference is I pass in the texture, and then I have this function actually get the normal from the texture, and then it does all the multiplication on that texture. So this essentially creates the tangent and normals and all this other stuff, and does all the math in the fragment shader. And what this does is takes the normal that is in tangent space and then brings it into world space, and then you can just use your regular code. For like I said, like the math mostly doesn't change, because as long as everything's within the same space, the math stays the same when it comes to doing normal lighting. So, like I said, this is like if you're not worried too much worried about optimizing things, this is probably the best, quickest solution to do it. Like I said, doing everything in a fragment shader. If you have deferred rendering, this might work out pretty well. Actually, no, never mind. Never mind that, because you have to use this to save the normal information into deferred rendering. So scratch what I was about to say. Which is going to be a future video, deferred lighting. I'm almost done making that. I'm just 3 videos behind. Yeah, and that's it. That's all to it. And if you really care, fragment version. Like I said, it all works. All the tests I showed you for the first one works. Yeah, and just for fun, I got the Mars texture and Mars is normal, which is barely noticeable. So I'm kind of disappointed that the normal for Mars, the only normal information you kind of see is in this direction. You probably can't tell, but it's very, very small. But so I just did Mars with the normal mapping, which is, like I said, it kind of sucks because there's not really much to it. It's hard to tell because the normal maps aren't that detailed for this planet. But here you go. Like I said, we're doing all this planet stuff, so they still had information things. So I just wanted to throw that in there just for fun. So you can have all this stuff to look at and test out and play with and whatnot. Maybe you can kind of do some things to increase the normals. Maybe, I don't know. You can't really increase the normals. So yeah, there you go. That is normal bump mapping in its, I guess, almost fullest thing you can do. Like I said, we did all the math of calculating the tangent, normal, and binormals, or bitangents. I keep switching them over. Sorry. We used the matrix 3 method. We did the quaternion method, and then we did the fragment method. So there's all different ways to do it. And like I said, in the previous video, we did the height map method, which we convert height map information into normal information for lighting. So yeah, that's it. My throat's starting to hurt, and I'll just leave it at big giant planet rotating. So see you guys at the next video. Next video will be fun. I like that one. See ya.